All right, 6.6, we're going to distinguish between linear and exponential growth. So, given table of values, we're going to be able to determine whether these quantities represent something that's a linear model or an exponential model. And just a couple things to remember. Linear growth, remember this is what you did in IM1 when you talked about equations of lines. They happen at a constant rate because you're just adding the same value repeatedly, okay? You're just adding a number over and over again. And in a linear model, you're adding close to the same number over and over again. Because it's in real life, things don't work out perfectly, but they could be represented closely with linear or exponential models. An exponential model, the rate is always kind of changing because you're multiplying by the same value repeatedly. So it doesn't look like a line. It grows kind of like this. So let's talk about that. Here we have, it says the number of branches of an oak tree and a birch tree since 1950 are represented by the following tables. Alright, so let's look at the oak tree first. Well, let's go ahead and read the directions down here. Determine whether each table represents a linear or exponential growth and write a function for each tree, O of t and B of t, that best models the number of branches based on time t in years. Okay, well, let's look at the oak tree first. And we're going to ask two things here. We're going to ask, hey, what number does it look like we're adding every time? And then what number does it look like we may be multiplied by each time? So the red will be if we added, and the blue will be if we multiplied. Okay, use a little star for multiplying. All right. So this is pretty easy, right? We could just kind of see what did we add to go from 34 to 46. Well, that would have been 12, right? And to go from 46 to 59, notice all I have to do really is subtract the second number from the first number to get how much we added, right? So this is 13, and then this is 11, and then this is 12. And so even though this is one above 12, and this is one below 12, on average, we added 12 every time. In fact, if you were to add these numbers up and divide it by 4, you would get exactly 12. So on average, we added 12. Now, how can we calculate what we multiplied by each time? Well, just like we could take the first number and subtract the previous, we could take, the second number and subtract the first. We could take the second number and divide the first. So let's go ahead and do that. 46 divided by 34. And we're going to have to round here because we're not going to get nice even numbers. It gives us about 1.35. And then if I was to do 59 divided by 46, I get 1.28. And then if I get 70 divided by 59, I get 1.18. So these numbers seem to be going down. These are changing, where these seem to be staying the same. And then I could do 82 divided by 70, and that's 1.17. Okay, so these numbers are changing quite a bit, where these ones, they change a little bit, but they on average, they stay right around 12. In fact, if we would have added 12 every time, we would have still ended at 82. Okay, let's go to the other tree, and let's do the same thing. Okay, so we got adding, and we got multiplying. Okay, let's first see what we get when we add. So 33 minus 8 to figure out what our first addition would have been. It would have been 25. And then 128 minus 33. So the next time we added 95. And then 512 minus 128. We see 384. And hopefully you see something very different about these numbers when we're adding. 2049 minus 512, and that's 1537. Okay, these numbers are very different, right? We'll talk about what that means in a little bit. Now let's talk about what happens when we multiply. Again, we're just going to divide by the previous number. So 33 divided by 8 is, I'm going to probably just do one decimal here, 4.1. Okay, and let's do 128 divided by 33, 3.8. Actually, it rounds to 3.9. Okay, let's do 512 divided by 128. It's exactly 4. Again, remember, I'm just dividing the second number by the previous number. And then finally, 2049 divided by 512. That is pretty much exactly 4. It's 4.002, so I'm just going to say 4. All right. Now we've got quite a bit of information here about both of these models, and we could discuss each of them. What I want to point out on the oak tree is that it looks as though we're pretty much just adding 12 every time. Multiplying by a number doesn't really work here because that number is different every time. So look up here. Does this look like we're adding the same value repeatedly, or does it look like we're multiplying by the same value repeatedly? Well, to me, it definitely looks like we're adding. So I think the oak tree is linear. We'll talk about how to write a linear equation in a second. Okay, what about the birch tree? Does it look like we're adding the same value every time or multiplying by the same value every time? Well, it definitely does not look like we're adding the same value every time. But yeah, on average, it looks like we're multiplying by 4 every time, right? I mean, this was 4.1 and this is 3.9, but they all look like they're right around 4. Here, it was 1 point something, but it constantly was getting smaller and smaller and smaller. So this is not a constant number that we're multiplying by. So we're not multiplying by the same value repeatedly. And what I mean by changing rate is the number in between, or this number that we're adding each time is changing. So this is definitely a changing rate. This is multiplying by the same number every time. So this is exponential. Okay, now it says determine whether each table represents a linear exponential growth. We got that. And write a function for each, O of t and B of t. That best models the number of branches based on time t in years. Okay, let's do the oak tree first. Because even though you haven't written the linear equation in a while, I think it's going to be pretty simple. I do want to point out something. If you look here, we're adding an average of 12, but we're adding an average of 12 every 3 years. So a way to think about this is we're adding 12 branches per every 3 years, right? Well, if you wanted to get a simple rate that's based on 1 year, this would reduce down to 4/1 branches per year. And so this little rate here is kind of like a slope. And so that's actually what we're going to use for our slope. Remember, if you go back, we use m for slope. Okay, because it's a rise, you could say, of 4 branches per every 1 year. Okay, so I'm going to write the number of branches we started with, which is 34. And I'm going to say, hey, plus we're going to add 4 branches for every 1 year. And t is in years. So there we go. We've got a model. It's not perfect, but it should, for the most part, get us really close to these numbers here. And it does work for several of them. So this works. All right, let's talk about the birch tree. For the birch tree, I'm going to first just remember the basic exponential model looks something like this, right? It looks something like that. And the important thing here is, remember, this little table goes every 10 years, okay? So it's multiplying by 4 every 10 years. That's important. So even though we're going to be multiplying by a factor of 4, we're not going to have just a typical t up here because t represents years, and we need to be able to plug in a 10 here for this to just have an effect of 1 multiplication of 4. So remember, p is our starting amount. We started with 8, so let's go ahead and do that. We have b of t equals 8. And instead of 1 plus r, a way you could think about this is that we're adding 300% every time because we're starting with the initial amount and then we're multiplying it by 4. So that's like if you multiplied it by 3 and added it to the original, it'd be the same thing. So this is like saying 1 plus 3 for 300%. Or you could just say 4. That's the same thing, right? If you multiply it by 4. Now, you're only multiplying by 4 every 10 years. So you want to be able to plug in a 10 for t here, right? And only get a 1 in the exponent because you're only going to multiply for every 10, you're only going to multiply by 4 one time. So how could you plug in a 10 here and get a 1? Well, if you take this t and divide it by 10, 10 divided by 10 would be 1, so this would work, right? If you plug in 10 for years, 10 divided by 10 is 1, 4 times, or 4 to the power of 1 is 4, and 4 times 8 is 32, and so that should work. In the same way, if we plug in 20, right, for 20 years, 20 divided by 10 is 2, 4 to the second power is 16, and 16 times 8 is 128. So this model looks like it's going to work pretty well for us. Okay, so we've come up with a model that represents the exponential growth, and we came up with a model that represents the linear growth. If you've been doing the rest of the notes, this one might actually seem easier for you, and this might be kind of hard because you forgot about things like slope. You're typically not going to have to do this, but I just kind of want to show you that you can. You have the ability to do that. So, all right. Example number 2, somewhat similar problem. It says the temperature of a glass of warm water after it's put in the freezer is represented by the table below. Which model for C of t, the temperature of the glass of water, t minutes after it's put in the freezer best fits the data? So again, we want to see, are we adding or subtracting the same value over and over again, or are we multiplying or dividing the same value over and over again? So let's just let's give it a shot. Again, I'm going to just go to my table, and I'm just going to see what's happening. One of the first things I noticed that I didn't point out to afterwards is that it looks like we're changing 2 minutes every time, and that's kind of important to keep in mind, right? So one of the things we could say is that the change in x equals 2. That little triangle x or delta x just means the change in x equals 2, because every time we're changing by 2. Just something to think about. All right. Now we're going to look at the change in temperature, right? And how is it changing again? Let's do addition on this side, and let's do a multiplication on this side. And it doesn't look like we're actually adding, right? I mean, or you could say we're adding negative numbers because we're going down. So 64.3 minus 80 is, and I'm just going to write the number right here, negative 15.7. So 80 minus 15.7 is 64.3. And then 52.7 minus 64.3 would give us negative 11.6. And then 42.6 minus 52.7 equals negative 10.1. 34.4 plus 42.6, negative 8.2. And then lastly, 27.5 minus 34.4, negative 6.9. Okay. This definitely does not look like a linear model because we are not adding, even though we're adding a negative number, that doesn't matter. We're not adding the same number every time. It starts off pretty big, it ends up down here at 6.9. It gets smaller and smaller every time. It's not constant rate. So maybe we're multiplying by a similar number every time. And we could be multiplying by a fraction. That's okay. That'll just give us a smaller number. Let's go ahead and do the same thing. So 64.3 divided by 80. And that gives me, I'll do 2 decimals here. So that gives me about 0.80. Okay, 52.7 divided by 64.3. 0.82. So again, what I'm saying here is I'm saying I did 64.3 divided by 80 and I got 0.80. That means 80 times 0.80 would give me 64.3. And then 64.3 times 0.82 would give me 52.7. So that's how I'm just dividing the lower by the one above it to find out what I need to multiply by to get there. Maybe if I do little like arrows like that, you could see we're multiplying. Okay, 42.6 divided by 52.7, 0.81. Okay, see, so we're getting somewhere here. 34.4 divided by 42.6, 0.81. And then lastly, we could do 27.5 divided by 34.4. And I get 0.80. Again, I rounded to the nearest 2 decimals. Okay, yeah, these look like we're definitely multiplying by something very similar every time. Over here, not so similar. So this tells me that it's definitely a exponential model, not a linear one. So I'm going to look over here, And since I know, I'm pretty confident it's exponential, I'm going to go ahead and take a look at my equations that they give me and see if I can rule any of them out. Any ones that don't have a variable in the exponent, like these guys and these are linear. So I already know it's not linear, so I could just go ahead and just cross these out. Now I'm really just debating between two. And now I can see that on average, if I was to average these, it'd be really close to 0.81, because 0.81 shows up twice, and 0.82 and 0.80, 0.81's right in between there, but then you just have one low one. So this 0.81 is a pretty good estimate as my rate here. And so it seems as though you'd be like, oh, well, there's 0.81 right there. Let's just go ahead and pick it. But there's one little curveball in this problem, and that is that, remember, our change in x was 2 each time. And so that creates a slightly different problem. So there's a few ways you can think about this, but instead of multiplying it by 0.81 each time, you're really multiplying it by something twice. And so you could think about it as, okay, what times itself twice gives us 0.81? Well, 0.9 does, right? 0.9 times 0.9 is 0.81, just like 9 squared times 9 squared is 81. So that's one way of thinking about it. The other is you could go ahead and write this your exponential model like we've been doing. Okay, so let's just write it out. Well, we know we're starting with 80 degrees. And we said we're going to multiply it by, let's just go ahead and multiply it by 0.81. But remember, when we plug in a 2 for t, we want it to equal 1 now in the exponent. So it would have to be t divided by 2. And we can do what we've done in other equations and kind of play with this a little bit. This is like saying 80 times 0.81 to the 1/2 times t, which means then that I could actually just bring this 1/2 inside and do 0.81 to the 1/2. Well, hopefully remember that's just like saying the square root of 0.81, and we know what the square root of 81 is. It's 9, so the square root of 0.81 is 0.9. So this becomes 80 times 0.9 to the t. And so that's another way that we could find the correct answer here, right? So this definitely seems as though this is the correct answer. So be careful. There's going to be ones that look right, but you got to think about it. Think about it. Is the x changing for every one, or is it by changing by something else? If it's changing by something else, you got to think about it a little critically. Maybe rewrite your equation, or think about, what's really happening for every 1 minute instead of every 2 minutes. So that's one of the little curveballs they're going to get you. Don't fall for that trap. All right, guys. See you on the next video.